Okay, earlier today, Miklos said that every talk should have a joke and a proof. Well, this is going to be a serious talk, so we'll have a proof and also an unsolved problem, which I think every talk should have. And but I don't think there are going to be any jokes. Yeah. Anyway, there's sort of two languages which are related. Now, in one language, one talks about representations. Of groups. In the other language, you talk about group actions. And these are really the same things. We can talk about a group action. Let's denote it by xg, where g is the group and x is a certain kind of a space. And so when x is let's make it a compact topological space. So this is the context of what we call topological dynamics. If X is a measure space, really a probability space where the total measure is 1, and G measure preserving action, well, this is ergodic theory. And if X is a linear space, Xa equals V, which would indicate a linear space, and G is a subgroup of GLV, invertible linear transformations, then we're used to talking about representations. And we talk about a representation of G. Now, all these situations, one can look at minimal such objects. Perhaps the most familiar one is in group representations. We talk about irreducible representation. And in certain cases, every representation is built up of irreducible representation. For example, for a compact group, the space can be decomposed into a sum of spaces in which the group acts irreducibly. When in topological dynamics, one is used to talking about a minimal action. And there it's not true that every action is built up of minimal actions. I mean, for example, just for a simple case, we can consider where the paths are sort of spirals which on one side converge to the center and the other side converge to the circle, and you move around in such a way, then there are this contains two minimal sets, namely the bounding circle, and the fixed point. But otherwise, there are no minimal subsets, and so typically you cannot reduce. Space is not the union of minimal subspaces, but it still it's of interest, and probably the most interest, to study minimal actions. Minimal action is is characterized by the fact that every orbit is dense. because the closure of an orbit is a subset which is invariant under the group, and by an orbit I would mean G acting on a point X, and the closure is a closed G invariant set, and if the system is minimal, then this has to be a whole space, and that means that every orbit is dense. And conversely, if every orbit is dense, then you have a minimal system. And in ergodic theory, what corresponds to minimal action is an ergodic action. Which says that there's no really proper subset which is invariant under the action. That's up to measure 0. So you have, again, the notion of minimality or irreducibility appears there. Now what we want to do, the first thing I should have said is that what I'm going to say is join with Elie Glasner and Benji Weiss. So we're going to study something called an affine action. So X here, X will be denoted usually by Q, a compact set that has additional structure. It'll have a convexity structure, a compact convex set, which is usually, in our situation, it's usually in the dual space to some Banach space. And the topology will be the topology that it inherits from a Banach space. In other words, we say that Qn converges to Q if for every element in X, every U in X, Qn of X converges to Q of X. And what we're interested in are irreducible actions. We'll say that action is irreducible. First of all, to be an affine action, every element G in Q preserves the convex structure. So what that means is that G of, say, AX plus 1 minus AX, 1 minus AY for A between 0 and 1 is the same thing as A GX plus 1 minus A GY. By the way, the notation that we're using is when we speak of an action of the group, it'll be convenient to think of to write. You have a map, of course, from G cross X to X, so that the action of G on a point X we just denote by GX. That will be convenient. You should write it as a more specialist likes TJ of X, but it'll be convenient just to write it this way. Now this can be generalized. There is a notion of the Barry center map, which takes the probability measures on Q into Q. Or let's write it this way. Beta, Barry center map, takes the measures on Q into Q. So this comes from a trivial 2-point measure concentrated on the point probability measure at 1 point. And this is, in order that you get the measure, you have, in other words, this comes from the measure A delta X plus 1 minus A delta Y, but more generally, a in order to preserve the convex structure, you can actually say the following. So for an affine action, G of the beta, the barycenter of an integral of, say, y d nu y, where nu is a probability measure, this over q, is the same thing as the integral of beta if the map is, you have pi, this is the, it's the same thing as the integral of y with respect to, G, in other words, G preserves the convex structure if beta of gy integrated over nu is the same thing as the integral of gy, or let's call it gz, integrated with respect to the barycenter of nu of g. G of z. With respect to the barycenter of nu. Anyway, so we're interested in irreducible representation. In other words, we say that this action, we call this an affine action. The affine action is irreducible basically if it's minimal. If whenever Q prime contained in Q is closed, convex, and G invariant, then Q prime equals Q, or it's empty. Any non-empty set, which by itself, in other words, you could replace QG by Q prime G. You could call that a subrepresentation, and there's no non-trivial subrepresentation. Then we say that the representation is irreducible. Now, we want to look at Lie groups. G should be a Lie group, and what happens if G is a compact group? Well, compact groups, if G is compact, it has what can we call the fixed point property. Which in fact is equivalent to saying that it's an amenable group. Then it's easy to see that for any take any point x in Q and integrate, look at gx dm of g, or dg, actually just say where this dg is the Haar measure, the Haar measure on G, and this will be a G. This will be invariant under all the elements of the group, because the harm measure is left invariant, and the closure, so this is a point which is this is a fixed point. This is a convex. This is sort of a generalization of a convex combination, and you might say this is the barycenter of the map. The barycenter of the measure that you get by putting mapping G into Gx, and the measure, the harm measure, if we denote that as mg. So this map, the barycenter of this map is an invariant, is a point invariant under G, and this is a probability measure, and okay, so this is the barycenter, and so there's no interest in compact groups because they all have a fixed point. So the only irreducible affine action is trivial. Is the trivial action of where the convex set is a point, Q is a point, and the action, of course, keeps the point fixed, and that is a convex set, but in a trivial way. So for compact groups, it's not very interesting to look for irreducible representations. So we want to look at a non-compact group, and we take the simplest, in some sense, the simplest non-compact Lie group, and you might, and that would be the PSL2 and this is going to be the group that we're interested in. G equals PSL2R, which is, in other words, the 2x2 matrices, basically of determinant 1, where you identify minus the matrix with the matrix. Well, this can also be seen, in other words, this can also be seen as the Möbius group. This is the same thing as the Möbius group of automorphism or analytic automorphisms of the upper half plane. And these all have the following form. G of Z has the form, say, alpha Z plus beta divided by gamma Z plus delta. You have to include the point at infinity in this in order that this be defined. And it'll actually be a little bit more convenient for us to look at the Möbius group and identify the upper half plane with the unit disk. And so this is the same thing as, let's just say, the Möbius group of the unit disk in the complex plane. Here the transformations have this form. G of Z is some e to the I phi times Z minus alpha 1 minus alpha bar Z, and it's where alpha is less than 1. And so alpha is the point that goes into 0, and you can see that this preserves this unit circle, and so it's an analytic transformation of the inside of the disk to the inside of the disk. And this is particularly convenient because there's a simple subgroup. This has a, let's denote by K, this subgroup, the compact subgroup, of transformations, g of z will denote it by k. K of z is just say e to the I phi times c. Rotations around the origin. So we're interested in the irreducible representations of this group. Now you can ask, well, show me one irreducible representation of this group. And it turns out that every bounded harmonic function in the unit disk gives us an irreducible representation. And let me explain why. This is sort of a basic fact. This is not a new statement, it's just something that was known and in a different context. So suppose H is a bounded harmonic function in, say, D, which is the unit disk. Now our group G is transitive. It moves any point to any other point. And in particular, well, we can write, we have the following formula, which let's define H tilde of G to be H of G operating on the origin. So I have a function on the group now, and in some sense it's more interesting to study this function on the group than to study harmonic functions in the disk. So let's see why. Let's consider the integral of H tilde k g prime, or kg, let's say, dk over the group, over the rotation group for fixed g. So we're rotating. What we have is some point. Now we have g of 0. What h tilde means, we put in a 0 here. So g of 0, let's say, is this point. And rotating it by k means we're looking at this circle. And then we're averaging. Well, the average, this is a very well-known property of a harmonic function, that the average over the boundary is equal to the value in the center. So this is h of 0 itself. And
no, of 0. H of 0. H of 0.
Okay. Now the point is that H, now this is also a matter of notation, will denote for any group, if we have a function on the group, G, then we'll denote by f k, or f gamma, let's say. This will be f of gamma g. And we'll denote by gamma of f, putting the gamma on the left side of f of g, we'll denote f of g gamma. Now the reason to do this is because then it's consistent that if I would write here gamma 1 times gamma 2, then this would be the same as gamma 1 after gamma 2 on this. So we can look at so consider the group itself acting on bounded functions on the group. So consider G acts now on L infinity of G by f goes into gf. Now I claim that this function h tilde that we get is going to generate an irreducible convex set inside L infinity with respect to this weak topology that we defined. And the reason for that is that if H is harmonic, so is H composed with G, or HG, but then this formula that I get H of 0 tells us that the integral, and so H tilde of applying to G of some G prime is the same thing as means H of G G prime of 0, and I'm sorry, G H tilde of G prime, which is what I'm really interested in, is H of H tilde of G prime, which is H tilde, which is H of G prime 0. Now if I integrate this with respect to K, in other words, look at K H tilde of G prime dk, then this will be H, the integral of H G prime K of 0. And now replacing H tilde by its translate on the left, so this will give me that 8k integral with respect to k of H tilde, this is to the right, of H tilde G prime K G dk. Now I'm really looking at the function hg prime. This is a function hg prime, and the integral over k, g is the same thing as if I replace as the h tilde or h of so I'm looking at the circle, so it's the same thing as h of g prime at 0. Or h tilde times g prime, h tilde of h tilde g prime. Now if I, instead of taking a single G, I take a linear combination of different G's here, I would still get the same result. If I take a convex combination, I would still get the same result. Let's write that integral over k of sigma, say ai of h tilde g prime k gi dk is the same thing. I haven't changed anything, but it's going to be where this is a convex combination. This will be the same thing as, this will again give me h tilde of g prime. Now, so if this is true for all convex combinations of gi, I could write this as the integral of sigma ai Now, with our notation, gi acting on h tilde of g of g prime of g prime is the same thing. This integrated h tilde is g acting on h tilde, and then I'm looking at k of this. So the integral. So for any linear combination, convex linear combination, so let's suppose that f is a linear combination equals sigma ai of h tilde of gi of h tilde. So what we've shown here is that the integral of f k of gi of f. So if I write here that k of f acting on g prime, this integral is the same thing as f for f. If I take f to be this is the same thing as h tilde of g prime. I hope I'm not getting things mixed up here. Anyway, this expression is in the convex. I mean, this integrated over k is a kind of generalized convex combination of the kf. Of the k, well, f here is h tilde. No, f. I'm sorry. This is f. F is this, and this gives me back. Yeah, this gives me h tilde. So h tilde is a linear is a generalized linear convex combination of other expressions of this type. So if v of h tilde is the closed convex set in L infinity spanned by and G invariant spanned by the translates of all the translates spanned by the different G of H tilde, then from any function that's inside here, for any f belonging to v h tilde, we get that h tilde is again a combination of these expressions. So that implies that this vf tilde, this vh tilde, is irreducible. Is irreducible because from one of the points from h tilde, which lies here, and I look at anything that it generates and take f belonging to v h tilde, then this implies that h tilde belongs to v of f, of the space generated by f. And so from anywhere you can get from h tilde, you can get back to h tilde, and that implies that it's irreducible. In other words, this space is from any point, from one point you can get to any point, then from that point you get back to this point. So therefore, you think about it for a minute, then it clearly implies that this is irreducible. So for every bounded harmonic function, you get such an irreducible representation. So so this is something that we knew.
Is it minimal?
Question?
Minimal?
Well, irreducible. In other words, because it's the same thing here. Minimal and irreducible mean the same thing here. So I should say my conjecture was, and this implies that there's certainly many irreducible representations. And I thought I thought I was able to show that there are at least two different ones, and it looked to me that there should be at least an infinity of them. And the question was, since there are a continuum of harmonic functions, there should be a continuum of different irreducible representations. Now, what do I mean by different? In other words, non-equivalent. What do I mean by equivalent? Or to this, you have to understand what is meant by a homomorphism or an isomorphism. So first of all, what do we mean by a homomorphism of two actions, between one action and the other? So if you have Q and G acting on it, and say Q prime and G acting on it, and and you have a map Q to Q prime, which preserves the convex structure, and so we call this map pi. So we say that there's a homomorphism or morphism if pi of, let's say, Gx is the same as G, that's on this side, and then you take pi of it, that's the same as G of pi x, where pi of x is in here, and so this sort of intertwines, pi intertwines the two actions, or in other terms, it's an equivariant map between the two G spaces. And so we say that that we have an isomorphism, or that two actions are equivalent if we have a homomorphism from Q to Q prime and another homomorphism to Q, and the combination of the two gives you the identity. There's actually an interesting important fact about these irreducible spaces. I'll call this irreducible affine space or irreducible affine system, is that between two irreducibles, if Q and Q prime irreducible, and pi 1 and pi 2 are both homomorphism from Q to Q prime, then this implies that pi 1 is equal to pi 2. Now this is unique. If there is a homomorphism, then it's unique. And that's, we take that as an exercise. It follows from the fact that they're extremal, that every one of these spaces that we're talking about is spanned by the extremals of the space. And an extremal cannot be a combination of two other points. And so therefore, if you look at pi 1 of x plus pi 2 of x, the average of this will give you another homomorphism. But if you look at it, what happens at the extremal point, if this first of all, the image has to be irreducible, because the image of an irreducible space is irreducible. And so in particular, it has to be onto. So in particular, some of these are going to be extremal points. But an extremal point cannot be written in this way unless the two are equal. So pi 1 is equal to pi 2 whenever this is an extremal. And since the extremals span the whole space, it implies that pi 1 is equal to pi 2. So one question that one can ask is, question 1, are all irreducible subsets, convex closed subsets, I'll just write that CC, convex closed subsets, and irreducible convex closed invariant subsets of L infinity of G. Do they all come? Are all of these? All of these come from, or do all irreducible representations come from bounded harmonic functions? And when are they, the second question is, when are they, if you could show, and that's not hard to show, that in fact every irreducible does come from, that in fact the answer to this is affirmative, because it turns out you take the k invariant, there has to be a k invariant element in this space, and that k invariant element is really a function on G mod k, which can be identified with the unit disk, and it's easy to see that it satisfies the right integral equation which characterizes harmonic functions. So there's really 1-1 correspondence between bounded harmonic functions in these invariant subspaces. And so when are they equivalent? So you expect them generally not to be equivalent. But in any case, you expect, or at least I expected, that you can at least form a continuum of non-equivalent representations. So the answer to our surprise was they are all equivalent. All equivalent.
Sorry, if you take function 1.
I'm sorry, what?
If you take a function 1.
I'm sorry, you're right. There's an
then
exception.
1 point.
Yeah, you get the trivial one.
Of course.
That's,
I just.
yeah. So the k in it turns out, and this turns to be the key of going from of an invariant subspace to a bounded harmonic function, is take the k invariant point, and it turns out to be unique. There's a unique k invariant point, because the general fact is a unique k invariant point in any irreducible subspace. So they are all equivalent, and in fact, all irreducible representations of this group G are equivalent. And this was quite surprising to us. So let me give an idea of why this is true. And this has to do with the notion of strong proximality of an action on a compact space. We say, well, first of all, proximality. We say an action xg, where x is just compact topological space. And here I'll assume that it's metric just to make things easier to write down. This is proximal if for any pair of points x, y, there exists a sequence Gn in the group with the limit of Gnx equal to the limit of Gny. So any two points come together in their orbits. Their orbits come together as close as you like.
Keep talking.
Okay? If for any probability measure, any nu, belonging to the probability measures on the space X, there exists a Gn, so that Gn acting on this measure converges to a point measure. In fact, converges to any point measure. I mean, if the thing is minimal, then for any z given beforehand. So you can get you can squeeze an arbitrary measure into a single point. Another way of looking at that is a more intuitive way of looking at that is to say that if I have a point, I've got the space, and I take a point in the space z, and take any neighborhood of z, I can squeeze most of the measure there exists, and I take an epsilon bigger than 0, so then there exists a g, so that, and call this neighborhood v, so there exists a g such that most of the points with respect to this measure, so I'm given a measure, an arbitrary measure nu, and an arbitrary neighborhood of an arbitrary point z, then I can squeeze most of the space into this neighborhood. And what do I mean by most of the space? Except for, with respect to the measure nu, it's 1 minus epsilon probability. So that that nu of G inverse of the complement of v, in other words x minus v, has measure less than epsilon. The points that don't get into v are of small measure. And that turns out to be the same as this statement of strong proximality. And has a very intuitive meaning that of the squeezing, a very strong squeezing property. It turns out that strong proximality does not follow from proximality. This was an example that Elie Glasner gave, I think, first example. So strong proximality is a very strong property, and you can take as an exercise, well, here's an exercise that if G is abelian, and action is minimal, xg minimal, it cannot even be proximal. Be proximal unless the space is trivial. With a single point. Okay. But for non-abelian groups, it's not hard to see that there exists strongly proximal actions. And in fact, here's a theorem for Lie groups. Well, groups G. If P is amenable subgroup, so you can think of P as stands for parabolic, and the action of G on G mod P is strongly proximal, then the action, their induced action on the space of measures on G mod P is an example. This is irreducible. This is not hard to prove, but not only is this the case, in fact, under these conditions, every irreducible action every irreducible, let's just call it Q, every irreducible QG is a factor of this, of P, of G mod P, this particular space of measures on G mod P. Now let's take the case of SL2, an immutable subgroup, of course, is the triangular subgroup of matrices. So we could take P to be a set of matrices of the form alpha, beta, 0, gamma. And G mod P then is basically the one-dimensional projective space, P1 of R. As you can see very easily, that these are the ones. These are the transformations which leave the x direction invariant, because you just multiply these by alpha. So you're it leaves the x direction invariant, and as the group acts on it, you get the whole projective line. In the situation if we're thinking of it as acting on the disk, so this G mod P will correspond to the circle, and then it's easy to see that the action of G on this is strongly proximal because of the fact that if I take something which moves the center very close to the boundary, then it'll take the whole circle and sort of squeeze it to a neighborhood in here. Well, obviously not the whole circle, but for a small part down here. And that shows that this is not only strongly proximal, which you see directly, but it's in fact the universal strongly proximal space in the sense that every irreducible, every proximal action is an image of this action, and therefore every irreducible, according to this, every irreducible affine action is an image of the action on this, measures on the circle. So our theorem that is a unique irreducible action will follow if we know that this action, that in this case, let's write it as P of probability measures on the P1 R on the projector space or projective line is these. If I show that this is the only irreducible space, and that's basically what we know. We know already that this is irreducible. Our claim that all the irreducible representations are equivalent is a statement that this is the only irreducible space. Now every other space is a factor of this. So we have to study what does it mean for one convex action, one affine action to be a factor of another convex action, affine action, and particularly we have the following theorem or proposition, which is based on another sort of a new kind of property. Here. We'll call something a linear Stone-Weierstrass. L stands for linear, so linear Stone-Weierstrass action. And this means that the Stone-Weierstrass theorem basically tells you that an algebra of functions which separates points is dense in the space of all functions. Uniformly dense. The linear Stone-Weierstrass property for an action on a compact space for xg, so I'm using x implies that I'm talking about a compact space, means this means that for any function f on x, f not equal to not a constant, if I take its translates, the space, and I take the linear space spanned by the translates of spanned by f composed with g, that this linear space is dense in C of x. Every continuous function can be approximated by an essentially linear combination of these translates. So that's a particular property, and the fundamental theorem here, or proposition, it's very not hard to prove, that that if it's an if and only if theorem, if xg has this property, let's call it just L Stone-Weierstrass, then any factor, if pi takes the measures, the probability measures on x to some non-trivial convex space, if this is a homomorphism, then the homomorphism in some sense is trivial, namely this implies then pi is 1-to-1. So that this representation is the same as this representation. And that follows, and it turns out to be equivalent to the LSW property of xg. So, if our claim is that the action on P of measures on this projective line, let me just write it as P1. If I want to show that this is the only irreducible action for our group G, then it's enough to show this will follow, since every action, because we said that this was a universal action, because this satisfies the property of, because P1 is the same as G mod capital P, and capital P is amenable, and the action on this is, the action on P prime is in fact strongly proximal. So this in fact is a universal irreducible action. Every other action is an image of this, but if it has the LSW property, then everyone has to be equivalent basically to this space. So the proof proceeds by showing that the circle, that if I think of the group G acting on the circle by Möbius transformations, those by the transformations I indicated, by the transformations W goes into, well, here will be zeta, think of zeta as a point on the circle, goes into zeta, well, e to the I phi times zeta minus alpha, 1 minus alpha bar zeta. This is the group of transformations of the circle. And if I show that this has the LSW property, that will prove our theorem. Well, this is in fact true, and the way the proof goes,